So today, Friday, we're going to wrap up chapter 2, and then I believe this is Monday, okay? That's Monday, exam 1, okay? Quiz on Friday. Quiz on Friday.
Tomorrow for 2 days, Friday.
It could be another quiz on another Friday, but chapter 2 quiz is just like it said right there on the syllabus. Okay? Let's see if I can get this to work. Old view. There we go. Okay. So, I was asked a very good question. It stumped me a little bit. I was asked, it stumped me in the sense that, it was a great question, and I needed to think this through a little bit better. So the question was, why do we care about hybridization? That was basically the question. Why do we care about hybridization? And then we went into geometry and everything. So this is, somebody has a caffeine cup or something somewhere. This is caffeine. And, you always see caffeine like this, right? This is just the first one that comes up. I have other examples here for you. But you always see caffeine like this. Who has the caffeine cup in here? Oh, you didn't bring it today. Oh, and how come you're not in the front row? What happened?
She took my spot.
He came in late. He came in late.
It's okay. I did not come in late. I had to rush over here from a piano lesson. I had 5 minutes to eat today, and that's all.
You have to kill me.
So you took his seat because he was hungry. That's even worse, I think. Okay, so if I take caffeine, you always see it drawn this way, right? You take caffeine, and I'm going to flip it over. It's a flat molecule. It actually is a flat molecule. Okay? And that's because, what is the hybridization of that carbon? It's got a double bond. So it's got a pi bond to it. It's got 1 pi bond to it. 1 pi bond to it. You have 3 choices. sp3, sp2, or sp. What has 1 pi bond? What has no pi bonds? Okay, you're on it today, I think. Okay, sp3. How many sigma bonds? How many pi bonds? sp2. How many sigma bonds? How many pi bonds? sp. How many sigma bonds? How many pi bonds? Four, 0, 3, 1, 2, 2. Okay. You're going to know that like it's your middle name. So, how many pi bonds to this carbon? It's drawn a little weird, but how many pi bonds there? 1. It's got a pi bond, right? It's a double bond. It's got a pi bond. That's what that means. Those 2 lines. One's, even though it's to an oxygen, we're going to talk about that in a little bit. And that one, sp2, right? Same. Look at those 2. sp2, that one, sp2. So what that does is it makes all of those p orbitals, like I try to draw poorly, how that one was going into this room and one's going into that room. So all the p orbitals, one of them's coming into organic and the other one is going into computer science, which forces that molecule to be planar. Okay? You have any other? Let me show you. Here is another molecule, doxorubicin. Anybody know what doxorubicin is? It's one of the most widely prescribed chemotherapy drugs. Okay? It's called the red devil. If you've had an aunt or someone that has had cancer and they said, yeah, I'm going in for the red devil, because it's red, the molecule is red, and it is really a horrible molecule to take. But it does put cancer into remission. So let's look at this. Let's look at this ring up here. What are all these carbons? sp2. What are these carbons? sp2. So those are all sp2. So would you predict, there's this out here, these are sp2. What about like this one? sp3. Yeah, sp3. And this one and these, those all do not have double bonds, so they are sp3 carbons. So would you predict this part of the molecule, this right here is my cursor up there, this part of the molecule up here, would you expect this to be flat or not? Yeah, just like caffeine, right? And what about this molecule, this part of the molecule over here? Would you expect this to be flat or not? Because what's the bond angle of an sp2? It's 120, right? But a bond angle of an sp3, like these down here, are 109. So if I take that molecule and rotate it, yeah, that part is flat. This part is flat, and this part is not. Okay? And so the way in which, so this you can't see this as well, but there is a reason why I called that molecule up. So here's, this is like a big molecule of DNA, but if I go up here and say, did this earlier, I say that's ball and stick, and I say bonds. I think I'm going to say bonds. Okay, so here's DNA. You guys have seen DNA before. And so if you look like right into here, you can see, can you see that? Catch the lights for me. You can see right in here are the base pairs. Okay, this is when they did this ribbon is like the helix. So if you look inside, you can see the base pairs, and you can see them hydrogen bonding. Okay, and so this part of the molecule in there where the base pairs are, they're all, if you look at the base pairs, if I were to draw those structures out, they're all sp2 carbons, and so they're flat. And so that's why when they hydrogen bond, you have these two flat molecules coming together that then are set up to hydrogen bond. And that is why you get this helical structure in DNA, okay? One of the reasons. This part over here, the sugar part, is not. These are all sp3 type carbons. They're not flat, okay? So I couldn't find it, but there is a very good crystal structure. These are all crystal structures of the previous molecule that I showed you, doxorubicin, inserts itself into the helix of DNA. And the way in which that works, so kind of remember that. I'm going to call back up Rubicin here. Oh, we can call it donomycin. That'd be the same. Pretty close. So this, normally when I flip molecules around like this, people go, whoa. But you guys are just so used to video games. It's not, back in the 70s when I used to do this, people would go, whoa. I was not teaching in the 70s, sorry. So this part is flat, okay, and that intercalates into DNA. This part is the control. So when this part actually comes in, hydrogen bonds to the backbone of DNA, to the sugars, to the riboses, and then it allows this to flip inside and go into DNA. And so then if that's in a cancer cell, when it goes to be replicated, the protease, which one is it? When it gets unwound.
Oh, helicase.
Helicase. When it comes in here, it stops. It doesn't know what to do, so it doesn't unwind it. So that cell dies. Okay? If it's a hair cell, then your hair also falls out. That's not what happened to me, but that's what happens to other. Okay, so this controls everything. You can catch the lights, Jason. So whether or not something is an SP2, SP3, SP, I probably should start off my lecture by saying this controls all structure and function of organic molecules. So, do you believe me? Some more lights to come on. Go ahead and get, I think there's more lights to come on. Yeah, just put them all on. That way people don't go to sleep. There we go. All right, any questions before we get going? That was a great question. It just took me a day to answer it. 2 days. Yes?
Do you put out a study guide?
So my notes are, all my notes are on Canvas. I have the videos. I don't have a study guide, because I basically just do everything. Who has last year's exams? I know they're out there. Somebody has them somewhere. But there'll be questions like, I can post last year's exam. I'll post it on Canvas. And I'll post once everyone takes the quiz, I will post and grade the quiz. But there'll be, I'll have a big hairy molecule like that, and I'll say, is it SP3, SP2? I'll have to pick it out. It won't be that molecule. It'll be another hairy molecule. Okay. All right. Any other questions? Any questions on sapling? We're all good? You all shell-shocked? Yes?
It's about drawing resonance structure.
Oh, okay. Okay. How about we wait until the end? Because I'm going to go over resonance structures at the end of the lecture today.
Okay.
That'd be all right? They are right here on my notes.
Okay.
And then we can do, and then maybe that'll help, and then maybe it'll be specific. Any other questions on sapling? Did anyone want to throw their computer through the wall with something? Good.
That's just sapling.
It was just sapling because you got to draw stuff and be better when the technology gets to where you can think it and it draws it for you. That's going to change things. That's what they're doing next door. Figuring that out. Okay. So let's look at some weird carbons. Okay? Carbons that you will we will talk a lot about this semester, but it somewhat breaks the rules that we've kind of established, okay? And you just let me know if this is even possible. Okay. So did I miss any charges? So I put a plus charge there. Is that a plus charge carbon? If these are bonds to anything else, I could put R groups, hydrogens. I'll put little hydrogens. Hydrogens, R groups, anything can be bonded there. What's the charge of this carbon? What do you think? You said +1. That's what I had drawn there, so it's probably a good guess. So I got 3 electrons coming in from those 3 bonds. It wants 4. We're supposed to bring in 4, so it's missing 1, so it's a +1. Okay? What about this one? +1?
It's not charged.
-1? 0. It is 0. No charge. It has not. It does. Those two have not filled their octet. that one has, right? That one's filled its octet. What's its charge? That's a -1, yeah. And how about this one? 0. Okay. Those are actually things that types of carbons we're going to talk about this semester. Okay. They are not carbons that you'll put in a bottle. Okay. These are carbons that are going to be in the middle of reactions. So we're going to do a reaction, and we're going to have a starting material. We're going to have a product, and somewhere in between, it will generate these intermediates. Okay, and so they're high energy types of carbon. Okay. So I was going to say you could find them at the sun, but you wouldn't find them at the sun probably. I don't know, too much carbon. There's not a lot of carbon at the sun. But like, if you have a lot of energy, you can strip electrons off and have these intermediates. Okay? This is a carbocation. These are its names. Okay? This is a carbon radical. And anything that has an unpaired electron is a radical. Okay? You've heard of oxygen radicals, things like that? Yes.
Why is the carbon with the -1 charge, why does it have that charge? There's 8 electrons surrounding it.
8 electrons. Okay. So this one is a carbanion. Okay. And it has, so it brings in 1 electron from each one of those bonds, and then 2 more. So it has 5 electrons. So it has one extra than it wanted to bring in. That carbon got an electron from somebody else. Okay, that's a carbanion, and this is a carbene. Okay, carbene. And so, just to say those things are going to be, and it's important. Their shape and structure is important as well. Let's look at a carbocation real quick. So I'm going to take, so this is the carbocation. Okay, so I've got my, remember I have my 1s down here, and I have my 2s, and then I have my 3p's. Okay. We're not going to worry about the 1s. So when I ask you this on the exam and you don't show me the 1s orbital, that's okay. All right? You can just start off with a 2s because that one's filled. So how many electrons does a carbocation have? How many did it bring? Brought in 3. 1. That pen is dying. I think that one over there on the end is going to work. 1, 2, 3. That's the way you would fill those in. Okay. If I look to say, well, I need all 3 of those bonds are equal, so I'm going to put this in my orbital mixer and put my 3 electrons in, what configuration do I have? What configuration is that? How many orbitals did I mix to get 3 equal bonds? I had an S, one S orbital, right? And I took a P, and I took a P, and I put them in my molecular mixer, and I came out with 3. So what are they? I'm hearing lots of mumbling. Yeah, those are all sp2.
Does it matter if there's no pi bond?
And then that one's left over, right? What orbital is that?
The P.
It's a P. Okay? So your question is a philosophical question. Do you have an orbital if you don't have an electron?
Good.
Are you pondering? I'm going to take this up with Joe Bankard. Do you have a... Okay, no one knows the answer to that. All right? So the way in which you look at that, I would say that a carbocation would have a structure, and I'm going to draw it like every other. So it has this structure with that p orbital up and below. So this is coming out towards you, okay? And so I have drawn that p orbital up and down, and that is going to dictate reactivity of a carbocation. Okay, it's going to dictate when we get to chapter 4 and 5. It's going to dictate how we make a reaction go. We're going to make decisions based on these intermediates having their shapes. Okay, to come. But you should know, if I were to say hybridize a carbene for me, you should be able to, give it a shot. It's in my notes here too. So, actually, if you do so this is always sp2. You can do this one. You can put that electron in a p orbital or an s orbital, actually. So it's sp2 or sp3. All right. It's kind of a weird one. And the same with a carbene is sp2 or sp3, because you could draw it both ways. But a carbene is sp2, because you just have the 4 electrons. Yeah?
Can I backtrack a little bit? So when filling the orbitals with the electrons, I remember we had fill, in chemistry, we just filled s orbital first before moving on to the p orbitals. But in this, we only put 1 electron in that 2s, and then just
Okay, we could do it that way.
throw it out. It doesn't really change.
I could do that.
Is that changing that?
No. I can do it that way. I guess I should have done that orbital that way. So I could do it that way. It's still though wrong. Okay, it's not the right configuration for carbon, because it doesn't represent my bonding. So I have to. The reason, you are correct. And I don't know if you did carbon specifically or you did other things, but they're always saying, oh, fill the lowest orbital before. But there's this thing out there that also says that there's a pairing energy. This is a little more advanced. So there is a pairing energy. And so this orbital has to be high enough that the energy is conserved to be paired versus being a radical. Okay? That's out there a little bit. But obviously, if I hybridize them this way, you go, oh, yeah. But here again, I can put an electron up there before I pair it, because I can say the energy difference here is not great enough. Basically, I can manipulate orbitals any way that I want them to come out the way nature has them. So we look at carbon, and we know that it has four sigma bonds. So our theory has to be reevaluated, and we say we're going to hybridize. Yes.
Could you possibly do one of the ones that have the 2 possibilities so that we can see why? So are they equally correct if you put sp2 or sp3 for carbon, radical or carbon, whatever? And so if we had that on a test, would you accept either one of the answers? And why is it that way?
Oh, I might ask you why.
Could you show us then? Because
I won't
understand
have-
what's going on.
I won't ever ask you a question and ask you to give me the wrong answer. So, is that helpful?
I think you could demonstrate one of them, because I'm not understanding conceptually.
So it's just a matter of how you want to draw it. I mean, I can say, so I have 4 electrons, right? So I have 4 electrons. So I can say, I can draw those, I can say I have this configuration, or I can put those in my molecular orbital and say that they're all sp3. And I have 4 electrons.
And so are you saying in nature they occur both? Is that...
Based on what's surrounding them, what other things are hooked on there, they can be different. So, you know, they can be both. Is that troublesome? You all want to be doctors, right? You cut into a person, are they all the same on the inside? No, actually they're very different. Is that troublesome?
A little.
Yes.
First time probably. Okay. If you don't, this is like what I'm also teaching the baby GChem, Intro to General Chemistry, and it's folks that really haven't had much science in high school or anywhere. And so we're doing significant figures, and it's really hard. And I say to them, don't worry, the world is not going to come to an end if you don't know significant figures. If you can't hybridize orbitals at the end of organic chemistry, the world's not going to come to an end. But you may have to you got to memorize a whole bunch more stuff maybe. Yes.
So I don't know if this is like obvious and I'm just not understanding, but how would you fill it if there was 5 electrons? I guess I don't understand it, like how you would get sp2 or sp3 if there's 5. I guess I'm just not understanding how to fill it. So okay.
And how would you show it on a, when you draw it with your...
Or I could fill this one. Fill that one.
Okay, so you would do it the same, okay. I guess so.
Or I could hybridize it to be... So a question, you're asking what question I would ask, right? So I would say, carbene is an sp2 carbon. Show the hybridization. Well, if you show me this hybridization, it's wrong, because that's an sp3 hybridization.
Yeah.
If you show me the sp hybridization, it's wrong. So it'll be okay. It'll be okay. Now, what if I say, show me the hybridization of the oxygen on formaldehyde. So this is formaldehyde. Show me the hybridization of oxygen on formaldehyde. Well, it's got to come out to be, I'm giving you the structure. You have to get that hybridization. So here's my 1s, 1s1, 1s. My 2s, sorry, gosh. And my 2p, x, y, and z, right? So how do I fill those? How do I fill that? How many electrons does oxygen have? Well, okay, 8. So those 2, right? Oh, yeah, okay, forget about that. We don't need that. And so then we have how many? 6. Do you want to pair it or not pair it? Doesn't matter. 2, 3. So I got my 4. Okay, now I'm going to pair it. Okay. Is that so? This. So if I were to. So how many sigma bonds and how many pi bonds does that equate to? What's that?
3 sigma, 1 pi. Don't the 1 pair electrons count as a sigma bond.
Actually, it's 0 and 2 and 2 lone pair. right? That's a lone pair. What are you trying to do to me? Bond? You got to bond that up to something? You can't bond that. It's already full. You can't bond that. It's already full, right? I can bond that.
But still sp2 then.
And I can bond that. That's 2 pi bonds and 0. So that's really horrible. So what do we want to do? I need to get you know what? I'm gonna bring in my molecular what do I call it? Mixer, my molecular blender. I had a molecular blender. Okay? So how do I want to arrange this that it turns out that oxygen has 1 pi bond, 1 sigma bond, and 2 pairs of electrons? Because that's what it is. What's the molecular orbital, right? So, yes?
Okay, I don't know why I'm stuck on this, but why are there 2 pi bonds in that?
Because, how do you make a bond? What do you do? How do you make a bond? With what? With what? Another atom? Another atom that has an electron to share? Right? Another atom that has an electron to share? That's where it comes in. It's going to share right there. So some other atom, let's say it's carbon, let's say it's nitrogen. Those are going to bring in electrons that are going to share in those orbitals. And that's how you're going to get a bond.
But in the molecule, there's the 1 double bond,
Yes.
which is the pi bond.
Yes. It's actually 1 pi bond, 1 sigma bond.
Right. So then why is there 2 pi bonds? I don't know why I'm so lost, but I am.
This does not represent the proper structure for this oxygen.
That would be that.
So there's not 2 pi bonds.
Oxygen is that being hybridized.
This would be, we proved that this is not the proper hybridization for oxygen because this would be 2 pi bonds. Does not have 2 pi bonds. Right? Just hang with me. So, we're going to take, no, hang with me. Just wait. Too many questions. I might answer it right over here. So, we're going to take this. Oxygen here has a pi bond, a sigma bond, and 2 pairs of electrons, right? So what's a good way to hybridize that? How many electrons do I have? 6, right? Now, how many? So now this is an sp2, right? And an sp2, and that's a p, right? So what kind of bond, if I'm going to bring in an electron from another atom, what kind of I got it going the wrong way, sorry. I'm going to bring that into there. What kind of bond is that going to be? That's going to be a sigma bond. So I have one sigma bond there, and if I bring an electron here to make a bond from some other atom, what kind of bond am I going to make? The world did not change. What kind of bonds do you make with p orbitals? Everyone should say like amen. It's like second nature. You make sigma bonds with s orbitals and pi bonds with p orbitals, right? Okay. Sorry, that's a 1. So, does this describe my oxygen that I have up here? Oh, wait, I've got 1 pi bond, 1 sigma bond, and then I also have these two lone pairs, right? So I've got my lone pairs. I have 2 of those. Now, so what's the hybridization of that oxygen? What's the sp2? Because that best describes the bonding of oxygen. You can do this with every atom. You can do it with nickel. You can do it with iron. You can do it with nitrogen. I'm not going to have you do it with iron because that's like inorganic chemistry. But we might might have you do it with nitrogen. Okay? So I think the problem is you get very mechanical about molecular orbitals, right? And you say, oh, this is it, and here I put my electrons in, and I always fill it this way and I always fill this way, which really what it is, a molecular orbital is just a way to describe nature. Okay? So you don't say that an atom has to abide by your molecular orbital theory. Because atoms abide by the laws of nature. We're trying to describe them with a theory. Okay? And it works. If we use our molecular scrambler and tweak our theory. Okay? You have a question?
I do.
Or a groan?
So from last lecture, we had, if we have an S and then 3 Ps, partially at least, then we'd go straight to sp3 on the hybridization. Right.
On one of them.
Right.
Okay. So, like I can't do it with oxygen. But with carbon, and I had 4 sigma bonds, right? I have to make each one of those bonds equal. It's just how I can look at a carbon. If I look at methane with 4 things attached to it, all those bonds are equal. How can I prove that to you? Do you believe me on that? Do you just trust me? They have to be, okay? So if all those bonds are equal, I have to hybridize those. I have to hybridize these orbitals to give me 4 equal bonds. And then when I do that, it brought in 1 s orbital and 3 p orbitals. So each one of these is an sp3. That's the name of the orbital. It's no longer an S, it's no longer a P. It's a combination orbital. Okay? Yes?
If it's a combination orbital, does that mean it's between the S and the P?
In energy. Because we just say that energy has to be conserved. That's a law, so we have to do that one. So, yes?
So then, for oxygen and other atoms, what do you suggest? Is like a rule or not really for like how we should start out, like sp2, sp? Like for oxygen, you added 3 sp2s and a p, right?
How about that one? Did I break any rules? Did I break any laws? It's all, the octet's filled, right? It's just charged. Charge just means it has 1 more electron than it has proton. What do you think the hybridization of that is? So, figure out by now that it's got 1 sigma bond and 2 pi bonds. So, can I erase this? So, I'm looking at oxygen. This is oxygen, not carbon. Huh? No, he asked me a question. So, I could ask you what the carbon is as well. But we're doing oxygen. He just asked me what would oxygen be if it was something different. I was just, no, he did. So I'm going to say it's that. SP, SP, P, P. Now, how many electrons do I have with oxygen? 5. I only have 5 this time. So 1, 2, 3, 4, 5. Does that work out? Two pi bonds. Yeah, it works out perfect. Works out perfect. I was like, it has to work out. Because what am I going to get here? What am I going to get here? We're spending way too much time on this. I'm going to get a pi bond there, right? I'm going to get a pi bond there. I'm going to get a sigma bond there, and I have a lone pair. You could do all of them. You can do all of them. But you could hybridize those 4 orbitals any way you want to. And then if you move down to the Ds, you can hybridize those with the S's and the P's however you want to. Did Einstein do some of those? GChem? Harris. Did Harris do some of those? He could have. I know he knows how to do that.
Yeah.
Okay. All right, let's do resonance. I heard some good moans right at the end there, so I'm not going to try to confuse you anymore. Okay, I'm going to leave this up here because this is like the most important thing. Put a little star there. Okay, and it's on video, so I start it on video. Meaning you should know that. Right? Okay. Let's do resonance for a little bit, and then I think come with questions on Friday, okay? And I'm going to give the quiz. So I don't think I have much more to say about Chapter 2. There's some non-covalent interactions that are on my notes here that are interesting. But come with questions on Friday, and we're going to do some. I want to hear from you. What are your questions? If you don't, I'll have some stuff prepared if you don't have questions. But I'm going to give you the quiz in the last half of the class. Okay, so just be prepared for that. Otherwise, I give you the quiz. I don't want to cover any new material. That should be the culmination before we move into the exam. Okay. All right. Oh, I'm going to give you one. I'm going to give you. Okay, one kicker here. I got one. This was on my notes. Okay. Have I violated any octet rules? Do I have my charges all right? All my charges all right? This is a nitrile. Okay. You can put that in a bottle. What's my hybridization of those two things? What's the hybridization of carbon? SP. It's got 2 pi bonds and a sigma bond. Oh, wait, look. There it is. What's my hybridization of nitrogen? SP. And I could draw up the molecular, and you would end up with a pair. Okay? Okay. There you go. All right, so typically draw, like this is a carboxylic acid, okay? That's a carboxylic acid. But Not really. Because I have these pairs of electrons, and I can dump these electrons into here and dump those over to there and get a resonance structure. Well, okay, I cheated. I'm gonna change it up. I'm gonna change it up. I'm gonna take the hydrogen off. Okay. I'm gonna put a pair of electrons there. So I'm gonna say it's. So I'm gonna say I got that. Okay. This has a charge on it. That's a minus charge. That's a minus charge. It's actually the same thing with the hydrogen. I just would do it a little bit different. Well, that's a resonance structure, and what that really means is that the way in which I draw this molecule, that really equals that minus charge is distributed between both oxygens. That'd be another way of showing that. Okay? So that's a simple resonance structure. If I had, so this one I already showed you. So I can have this resonance structure and just drop all of these electrons. It's a real simple one. I'm going to do a more complex one in just a second. So I can just move those all around. I moved them to the right. You can move them to the left. Just the same, because they don't know. I get that. Or I can say all those electrons are in there, or I just make the circle all the way around. That's kind of how we draw that. Okay? But if I say draw the resonance structures, you have to give me this. Okay? Because those are the resonance structures. This is a summary of the resonance. These are the resonance structures. Okay? So let me change this up some. And then we're going to answer your question on resonance from Sapling. Okay? Ooh, we are going to combine some stuff here from the beginning of the lecture and hybridization and everything else right there. Okay. Okay, ready? Are you guys ready? What is the hybridization of these carbons? I heard an sp2. Okay? Remember, I'm going to give you a big hairy molecule that has those on there. Okay? What's the hybridization of that one? Remember, we did it. Look earlier in your notes. S, P, hold up fingers. Oh, you guys are just not vocal. Okay, I'm still figuring you guys out. You're just not vocal. Okay, it's sp2.
On that, do you just disregard the fact that it doesn't have a pi bond?
Doesn't have a pi bond, but it has 3 sigma bonds.
Okay, that's what matters though. Is
Well, we got to go back to the philosophical question of, do you have an orbital if you don't have an electron? Okay. The answer is yes, right now.
okay, that's fine.
So I'm going to say that there's an orbital in there, one going forward, one going back. Okay, so it's in the other room. Okay. So that orbital's in there, just imaginary there. So let's draw the resonance structure for that. How many are there? Okay, here we go. You ready? Got 5 minutes. Boom. I'm going to put that there. Okay. So what I did is I moved these electrons here. When I moved those electrons there, so I have just one hydrogen here. I still have one hydrogen, so I just have 3 bonds to that carbon, so it has to be a plus. Then I'm going to move these electrons here. Still just has one hydrogen there, so that just has one hydrogen. So now that has to be a plus. Okay? So there are 4 resonance structures for that one. That positive charge can be on this carbon, this carbon, this carbon, this carbon. There's a whole, and then there's a theory out there about the alternate charge. There's the alternate charge theory. We won't go into that. I did my first year seminar in graduate school on the alternate charge theory. But it does alternate like that. Got to think about that. Okay? All right. The more resonance structures you can draw on something, the more stabilized it is because you've taken that positive charge and distributed it over more atoms. So your overall effective bad octet is better. Okay, what's the sapling question?
It was about drawing resonance structures for an NO3 ion.
NO3. Oh man, that sounds hard. What was it? How many electrons did I have? NO3. Just the N.
It doesn't. You have to put in the electrons.
Oh, okay. Yeah, that sounds hard.
Thanks.
It doesn't have carbon. Who cares? NO3. Did it have an ion? Anything? It's a minus charge. It's got to have something. So it's got to say nitrate, nitrite, nitrous, something. Okay. So it's got to have a minus charge. So got to have some electrons out here, probably like that. 2, 4, 6. Probably like this, and then that is plus 1, 2, 3, 4, 5. Is that right? And then you just these electrons are going to end up around each one. But the way in which that works, here I'll draw one for you. These electrons dump into that bond. Those electrons drop out onto that oxygen. Okay, so it already had 2 pair on there. So then you draw that. Nothing changed there. That now has a double bond. And I took 1 pair away, so it just has the 1 pair. And then here I added a pair to that oxygen, so then that one becomes minus. Oops, wrong color. Okay, plus charges are always blue, so I'll put it in blue. And then you can do that one more time. So there's three resonance structures there. So if you got that wrong in sapling, it's probably because you had the wrong pairing of electrons, or you forgot the charge, or out here somewhere in the screen you push the button and there's a free electron out there somewhere in the screen. Seen that? Have you seen that yet? You like clicked out in the screen somewhere and it said, "Oh, that was an electron." And then it just says, no, you're wrong, you're wrong, because you have this radical electron floating around out there in the middle of space. Okay. If you got questions on sapling, email them to me. Class is done, but I'll take some questions. Still trying to fill you guys out. Yeah.